So in this video, we'll be going over the recoiling rifle problem. So there's a lot going on here with a lot of information. The first thing that I would suggest that you do is to highlight the important pieces of information in the problem. So we have a rifle. We're told the mass of the rifle is 800 grams. There's a bullet that gets fired from it, and that has a mass of 5 grams. We're told that once the rifle fires, the bullet travels at a velocity of 300 meters per second. So we're told what our system is to start. So our system that we need to look at for the first part is the bullet in the rifle. And we're asked to find what the recoil velocity is of the rifle. So we're looking for a velocity. What's going on in this problem is the bullets inside the rifle to start. They both have a velocity of 0 because they're starting at rest. And then after the rifle fires, the bullet goes off to the right. And to be able to conserve momentum, we know that the rifle needs to have a velocity to the left. And that's what this kickback is. You may have seen it in movies or in person. You know, the bullet fires one direction, so the rifle or the gun needs to kick back in the opposite direction. So let's start by labeling. We have a bullet with mass MB is equal to 0.00. Actually, we can just keep it in 5 grams. We have a velocity final at this point, VBF, is equal to 300 meters per second. What direction is that in? The first thing we should do, and I made a mistake here, first thing we should do is define a coordinate system so we can choose our given and unknown variables. So I'm going to choose to the right to be the positive x direction. And now we know that this velocity is going to be a positive 300 meters per second. And I think we're good in terms of those quantities there. Now we have the rifle. We're told that the mass of the rifle is equal to 800 grams. And we need to know what the final velocity of the rifle is. We're expecting that, again, we're expecting that to be in the left direction, which will be the negative x direction. We're told that, or we can assume that they're starting from rest at the start, so VB naught is equal to VR naught, which is equal to 0 meters per second. So what are we going to use to solve this? We're going to use conservation of momentum. Conservation of energy does not apply here because energy is not conserved. We're converting some chemical energy that we cannot access, into what this final energy is, so we can't use that. Now we can move on to the next part of the problem. We're asked, the hunter's shoulder stops the rifle. That's why the recoil hurts. What impulse must the shoulder deliver in order to stop the gun? So we're looking for an impulse. And then for C, we have, if the gun comes to a rest against the shoulder in 3 milliseconds, what is the force exerted by the shoulder on the rifle? And then we're asked the rifle on the shoulder. We'll be able to answer that last question fairly quickly. So what's happening here? We have the rifle's kicking back. It has a leftward velocity. And the shoulder is there applying a force on the rifle, getting it to stop. So we must have a rightward force from the shoulder. So I'm going to call that F sub S. That's acting on the rifle. Now, if I'm the one applying a force to the rifle, why does it hurt my shoulder? Now, the reason why that is, and this deals with the last question, is the idea of Newton's third law. Newton's third law is that there's these paired forces. So for every force, there's an equal and opposite force. So if I'm applying a force on the rifle, that rifle is applying a force that's equal and opposite on me. And so that force by the rifle on my shoulder is why it hurts. Okay, so it looks like we've got the problem set up. We just need to figure out what it is we're looking for. The first part, for part A, we're looking for the recoil velocity, which we've defined to be the VRF. We expect that to be negative and meters per second. The second thing we're looking for is the impulse. The impulse is equal to the change in momentum. And we expect that to be a positive value and be in terms of kilogram meters per second. And then finally, we're looking for the force of the shoulder, and we already discussed the force by the rifle. Force by the shoulder is going to be to the right, so it's going to be positive, and it's going to be in terms of newtons. So we can move down to the second part, planning the solution. So the first, for part A, we're going to be using conservation of momentum. We know that both the rifle and the bullet are at rest, so we can conserve momentum and solve for the rifle's recoil velocity. Then after that, we need to find what the impulse is to stop the rifle. And so there we're just going to take what the change in momentum is of the rifle to be able to solve for the impulse. And then from that, we know the time frame that the force by the shoulder is being applied to on the rifle. So we can determine what the net force is as a result of that change in momentum. So now that we have our plan in place, we can execute it. So starting with part A, we're going to use equation 1, which is our momentum conservation equation. The initial velocity of the bullet and the initial velocity of the rifle are 0, so the left-hand side becomes 0. And then we're left with the mass of the rifle times the final velocity of the rifle plus the mass of the bullet times the final velocity of the bullet. Solving for the final velocity of the rifle and substituting in our quantities, we find that the final velocity of the rifle is equal to minus 1.8, sorry about that, 1.88 meters per second. Now, one thing you might notice is, hey, you didn't convert the mass in grams into kilograms. The thing is, and the nice thing about the conservation of momentum equation is a lot of times you're not going to have to do that if you're dealing with the same units of mass. If one's kilograms and one's grams, then of course you're going to have to convert. But in this case, they're both grams, so they cancel out. So it's okay to leave them as is. In the end, you want to make sure that your end result that you're solving for has the correct units. We're solving for velocity, we are expecting meters per second, and we get meters per second. Coming on to part B. So for part B, we're asked to solve for the impulse that the shoulder must deliver to stop the gun. And so let's go ahead and draw out what's going on. Our system now is the rifle. This is our system for part B. We're not dealing with the bullet anymore. So To get the impulse, we need to solve for the change in momentum. And the change in momentum of our system is the change in momentum of the rifle. So we know that the initial velocity for this portion is the recoil velocity. So we have VR naught is equal to negative 1.88 meters per second. And then we know that the final velocity, VRF, is equal to 0 meters per second because the shoulder's stopping the rifle. So it must have 0 velocity. So now that we have that situated, we have our impulse equation, which is just equal to the change in momentum, where momentum is equal to mass times the velocity. The final velocity is 0, so we're left with 0 meters per second, minus, we have a mass of 0.8 kilograms, and this is a spot where you're going to want to convert. And then we have, again, our initial velocity is that recoil velocity, which is equal to negative 1.88 meters per second. Substituting in, you find that the change in momentum, or the impulse, is equal to 1.5 kilogram meters per second. After this, we're asked to find what is the force of the shoulder if the time frame for this motion on this part, delta t, is equal to 3 milliseconds. So the change in momentum is a result of a force being applied over a time interval. So we know what the change in momentum is. And what we're going to do is we're going to solve for the force by the shoulder, which is equal to the change in momentum over the change in time. Time is not a vector. We can substitute that in. We know the impulse from before, kilogram meters per second. We need to convert milliseconds into seconds. All that is just 0.003 seconds. And we find a force of the shoulder to be 500 newtons, and positive to the right as we expect. And then the final is, we found the force exerted by the shoulder on the rifle. What is the force exerted by the rifle on the shoulder? Well, we talked about this already. This is a paired force. You know, I'm applying it on the rifle must be applying it back on me. And that's from Newton's third law. Paired forces. So the force by the shoulder is equal to, or I'll rewrite this, the force by the rifle is equal to the opposite of the force by the shoulder, which is equal to negative 500 newtons. And that's our final result.